All right. So in Strength of Material 2, Lecture 10, we are going to be talking about torsion. This lecture outline is composed of introduction, assumptions in the theory of pure torsion, derivation of torsion formula. We are going to also talk about the torque transmitted by solid circular shafts and also torques transmitted by hollow circular shafts. We are also going to have a look at power transmitted by shafts and also some work examples as well. All right. So the objectives of the course is that at the end of this lecture, you should be able to understand the concept of torsion in circular shafts, understand the assumptions of pure torsion, and also derive the torsion formula. You are supposed to also be able to understand the power transmitted by circular shafts and also calculate torsion in circular members. In the introduction, we are going to be talking about Charles Augustin de Coulombs. Okay, he was born in he was born on 14th June 1736. He was a French physicist. He was a French physicist and engineer. He is the best known for his Coulomb's law used in electrostatic for finding the electrostatic force of attraction. Okay, yes, electrostatic force of attraction, or let's say repulsion. Let's take it one more last time. Charles Augustin de Coulombs was born on 14 June 1736. He was a French physicist and engineer. He is the best known for his Coulomb's law used in electrostatic for finding the electrostatic force of attraction or repulsion. Okay, yes. And the SI unit of electric charge, the Coulomb C. So he is the one who discovered it. He is the one who propounded the theory that led to the discovery of the Coulombs and was named in his honor. Okay, so it was named in his honor. He derived the torsion formula in about 1775. Coulombs leave a legacy as a pioneer in the field of geotechnical engineering for his contribution to the design of retaining walls. His name is one of the 72 names described on the Eiffel Tower. Okay, so his name is Charles Augustin de Coulombs. I believe today at least we have all learned something at least. So it is good to learn physics and become a physicist so that in future you can be able to help others. Yes. Okay. So in the introduction, members in torsion are subjected to twisting action about their longitudinal axis. It is It has wide engineering application, most common among them in transmission shaft, which is used to transmit power from one point to another. Solid as well as hollow shaft can be used for the transmission power. Yes, the torsion formula was derived by a French physicist, Charles Augustin de Coulombs, in 1775, as we just learned about him earlier. A shaft is said to be in torsion when equal and opposite torque are applied at two ends of the shafts. Most of the calculation we are going to be doing are going to be composed of the shafts. Okay, so as we are talking about shafts, it could either be a hollow shaft, it could either be a circular shaft. You should take note of some of these things so that at the end of the day, you don't find yourself wanted. Okay, we say a shaft is said to be in torsion when equal and opposite torques are applied at two ends of the shafts. Okay, yes, and a torque is a measure of the rotational force that causes an object to rotate or twist around its axis. So the torque is equal to So the torque is equal to the product of the force applied tangentially to the end of a shaft and radius of the shaft. Okay, so this is how the shafts look like. Okay, so this is a solid shafts. Okay, and we also have hollow shafts. Yes, I'll be showing you that in the next section. Due to the application of torque at the two ends, the shaft is applied to a twisting moment. This causes the shear stresses and shear strain in the material of the shaft. So we are saying that this is a solid circular shaft subjected to torsion. Okay, yes, a solid circular shaft subjected to torsion. And how did we say torsion is? We said torsion refers to the twisting of an object due to an applied torque. Yes. Okay, let's quickly proceed. And this is the proof of the torsion formula. We are going to be looking at it soon. Okay, but before then, these are some of the assumptions of theory of pure torsion. Okay, let's quickly have a look at that. And also, let's all remember to take a note and a jotter so that as we read or learn along, we can jot some important points that can aid our understanding later. Absorptions of pure torsion. The material of the shaft is homogeneous and isotropic. 2. The stresses are within elastic limit. That is, shear stress is proportional to shear strain, as we learn in first semester. Yes, if they say something is proportional, it means that as shear stress is increasing, shear strain is also what? Increasing. And that is the meaning of that. Okay. Cross section. In the third point, we are going to be looking at cross sections are plane before applying twisting. Moments remain plane even after the application of twisting moment. That is, no wrapping take place. Radial line remain radial even after applying torsional moment. And also, the twist along the shaft is said to be what? Uniform. Those are assumptions. And this is the what? The torsion formula we say is given as this. Okay, yes. So this is the shaft as we were talking about, and this is how the cross section of the shafts look like. Okay, yes, and this is the shaft itself. You can see we have over here a solid circular shaft subjected to what? Torsion. It's subjected to a twisting what? Twisting moment. Okay, so the torsion formula, the R is given as the what? The radius of the shaft, the L being the length of the shaft, the T being the torque applied to the shaft at end A. Okay, at the end A, and also this tau is maximum shear stress induced at the outer surface. It continues as that. Okay, so later you can take time and go through all of this, and you will see how the formula is being proved. Um, Without wasting too much time or beating about the bush, let's quickly take a look at this formula. Okay, kindly jot this formula down. Kindly jot this formula down. Okay, so this is the maximum torque transmitted by a shaft. This is the formula for calculating for the maximum torque transmitted by a solid circular shaft. Okay, yes, where the T is the hot torque transmitted by the shaft. The tau is the maximum shear stress induced at the outer surface, and D is the diameter of the shaft. Okay, and also for maximum torque transmitted by hollow circular shaft, this is the formula we use, where T is the torque transmitted by the shaft, The tau is the maximum shear stress induced at the outer surface. And then D subscript O is the outer diameter of the shaft, and D subscript I is the inner diameter of the hot shaft. Okay, so let's go through the power transmission. Okay, let's talk about the power transmission. Let's talk about the power transmission and the power transmitted by shafts. Okay, we say shafts are the medium to transmit power from the point of power generation to the point of its application. The power transmitted is the work done per hot seconds. A shaft may transmit power at more than one section to different machines. Also, the shaft may be subjected to different torques in different sections. In such cases, the principle of conservation of energy can be what applied. Usually, the shafts are designed on the basis of limiting values of stress and the angular deformation. Okay, and the uh, formula for power transmitted by a shaft is given as what? The angular speed times applied torque. Okay, and the torque in the question you may calculate for it before you can use it to calculate for the power transmitted by the shaft, or it may be given to you to substitute into one of them to find for the other. Okay, yes. So where the angular speed is the hot omega and the applied torque has a symbol for T. Yes. Also, we have to note that the angular speed has a formula of this. Okay, 2 pi n divided by what? 60. Where we say that the P is the power transmitted by a shaft in watts. In watts. And N is revolution per minute of the shafts in RPM. Also, the torque applied in what? Newton meter. And the omega is the angular speed of the shafts. Okay, good. From there, we can take a look at some work examples and see how we can apply them in our daily life to make life easier. So please, you can jot down some of these formulas we have looked at so far. First of all, let's say the first one we looked at. I want to number it. Okay, I want to quickly number them. The first formula you need now is this one. Okay, so let's say this is our first formula. After writing this, quickly write this and write the heading. That is the maximum torque transmitted by a solid circular shaft. Then also you come and write down this one, second. Okay, this is the also second formula you need, and that is the maximum torque transmitted by a hollow circular shaft. Okay, write this heading too. Then after that, you come and write down this formula too. Okay, so this is the power transmitted by a shaft is also given as this. So that is this formula too. You write this formula down, and this becomes our third formula. Okay, so this becomes our third formula. Good. From there, what do we do next? We are only coming to do some work examples. Okay, so that we see how, if the question is given, we can be able to apply that to make life better. Okay, so the first problem says that a solid shaft of 150 mm, a solid shaft of what? 150 mm diameter is used to transmit torque. Good. Find the maximum. They say we should find the maximum torque transmitted by the shaft if the maximum shear stress induced to the shaft is 45 Newton per mm squared. Okay, so the first thing we are supposed to pull down is our what? Is our given. Okay, the first thing we are supposed to pull down is our given. And the diameter of the shaft they told us from the question is what? You can see over here is what? 150 mm. Good. Also, the maximum shear stress. The diameter is just the shaft. Let's say if this is the anterior end, the diameter is just this. Okay, good. It's a circular shaft. So you have to see that it's in the form of a circle. Okay, yes. So you can just also pull down some sketches so that you can also get some additional marks from there too. Okay, it's in the form of something like this. That is how the shaft is looking like, and that is the diameter I just indicated in there. Good. So we said that uh, also it has a what the maximum shear stress. Okay, which is this? Which is this? Was what? 45 Newton per mm squared. Okay, yes. So that is what we have written here also. As simple as that. So from there, um, the maximum torque transmitted by the shaft, we said is given as what? T is equal to pi over 16 times what? Our maximum shear stress times the diameter cube. Okay, so it's just a matter of you substituting whatever has been given to you. Okay, once you know the formula that your T is equal to pi over what? That was the first formula we underlined. If you could remember, the first formula I told you to wrote to write. Okay, yes, times the this it was 45. Okay, the maximum shear stress was 45. Okay, so you write that down times your what? Your diameter. The diameter of the rod was 150. Okay, so at the end of the day, you just cube it. Okay, it's just a matter of substitution. We said that the pi is a constant, and the one that we are using is just three decimal places. Please avoid two decimal places at least. You can even choose to use four decimal places. Okay, yes, because for precision purpose, the more your decimal places, the more accurate your answer could be. Okay, but for the meantime, we are using 3.142. Okay, so in place of this, you can even put this value over there. Okay, as your pi. You can even put this value over there as your pi. Then at the end of the day, you are going to get your answer. But remember that because you're 45, okay, and your 45 was our maximum shear stress. Okay, our 45 was our maximum shear stress. So because of that, it's going to affect our answer for answer to be in Newton per what mm squared. Due to that, we said torque is also measured in what Newton meter. Torque is measured in Newton meter. So we have to convert this answer back into what? Newton meter. And in doing so, we just have to divide. Okay. So this was divided by what? 10 exponent what? 3. Let's all try that together. 298,244,53.13 divided by 10 exponent 3. And what are we going to get? We are going to get what? 299.45.313. Okay, Newton meter. Okay, as a result of we dividing it by what? 10 exponent 3 to change the answer from what? Mm to what? Meter. Okay. To change the answer from Newton millimeters to Newton meter. As easy as that. Okay. As as easy as that. As easy as that. As easy as that. So let's quickly look at the example two. For that one, we will be solving it systematically ourselves so that at least we can see how that can also be applied in real life. Okay, good. So the question says that the shear stress in a solid shaft is not to exceed 40 Newton per mm squared when the torque transmitted is 20,000 Newton meter. Determine the minimum diameter of the shaft. Okay, so we have to determine the minimum diameter of the shaft. Okay, so first of all, we are supposed to put down our given. The first thing we are supposed to do is put down our given. Okay, so in the given, we say we are just going to read the question back again and bring out the vital points. Okay, and also determine what they're actually telling us to find. Okay. So first of all, they say the shear stress in a solid shaft is not to exceed. So they say that this is the symbol for our shear stress, right? Okay. It's not to exceed what? 40 Newton per mm squared. Okay. And also, when the torque transmitted is 20,000 Newton meter. When the torque transmitted is 20,000 Newton meter. Okay. So our torque is equal to 20,000 Newton meter. So they said that the shear stress is not to exceed 40 Newton meter, Newton per mm squared. Okay. So from here, they say we have to determine the minimum diameter of the shaft. So they want the minimum diameter of the shaft. And the minimum diameter of the shaft, we assume that we don't know. Okay, so we put question mark. So it means that this is what the question is asking us to find. Okay, so we have to move to our solution. We have to move to our solution. But first of all, what did we learn? We learned that our torque, okay, our general formula is that our torsion is equal to what? Pi over what? 16. That was the first formula we wrote. I said we should write down. Times our shear stress, okay, multiplying the diameter what? Cube. From here, let's go back to our given and actually see whether all what we are having over here can also be found in the given. Okay, so we can see that our shear stress is 40 Newton per mm is over here, and the diameter is what they say we should find. Also, the T is the torque, is the that has also been given. Okay, the torque transmitted that has also been given. So it means that we have to make the subject so that we can be able to find for it. Okay. But before that, we have to make 16 the LCM. Okay. So we say that we have to find for LCM. Okay. And our LCM is going to be what? Um, Equal to 16. Yes. It's going to be equal to 16 because that is the highest common denominator. Okay. From there, um, if our LCM is equal to uh, if our lowest common lowest common is equal to 16, it means that we have to use it to multiply everything. Okay, we have to use it to multiply everything. So it implies that we are going to have t times what? 16, which is equal to pi over 16 times the tau times what? Um, d cube, all times what? 16. Okay, so from here, you realize that 16 will cancel 16. Okay, this 16 will cancel what? This 16. From there, we are going to get a relation such as what? 16t. 16t. 16t is equal to our pi multiplying the what? Shear stress times the diameter cube. Okay, from here, the only thing we are going to do is that we are going to use the diameter. We are going to divide both sides. Okay, we are going to divide both sides of the equation by pi and the shear stress. Okay, so this is how that is going to look like. You say we always have to repeat this step so that we don't lose marks. Okay, yes. And from here, we are going to divide here by what? Pi and the shear stress. We divide both sides because we want D to what? Stand alone. That is why we are doing this. So from here, these two people are going to take care of these two people. So you realize that finally our relation is going to become 16t all over our pi over what? Tau is equal to the diameter what? Cube. Take note that in physics, A is equal to what? B is the same as what? B is equal to what? A. So that implies that at the end of the day, the what I've written over here, if 16t over pi tau is equal to d cube, it means that what? D cube. It means that d cube is also equal to what? 16t over pi tau. 16t all over pi tau. Okay. So from here, uh, because the d is cube, we want the d to stand alone. In this case, it is just like d times d is equal to 16 t over pi tau. Okay, but we don't want it to be that way. So we have to take the cubic root of both sides to take care of the root sign. Okay, so we have to take the cubic root of both sides. Okay, we have to take the cubic root of what? Both sides. So at the end of the day, you realize that what this is going to take care of that. Okay, this sign is going to take care of this sign. So now we can say that the d is standing alone. Okay, so finally we can say that the d is equal to our d we are looking for is equal to cubic root of 16 t all over what? Pi tau. Okay, so you just have to learn the change of subject very well because you can be asked to calculate for any of them. Okay, so once you are good at the change of subject, you realize that you are not going to struggle much in your next stage. Okay, so just work on that. Better still, you can refer to the lecture video so that life can be easy. From here, it's just a matter of substitution. Okay, so you just substitute whatever you have into the equation so that life can be easier. Okay, so you are taking the cubic root of all of that. Okay, yes. So our pi, we say the pi we are using is what? So first of all, we have 16. Okay, multiplying what? Our 16 is multiplying the torque. And what was the value of our torque? It was 20,000 Newton meter. Our torque was 20,000 Newton meter. But in this case, we are looking for the what? The diameter. Okay, before we can use that, we have to convert it back into what? Newton uh, millimeter. Okay, due to that, in converting that, if you want to convert the 20,000 Newton meter into Newton millimeter, it means that we have to multiply it by 1,000. Okay, we have to multiply it by 1,000. So finally, we can say that the T we are using over here, our T is going to be what? 20,000. Okay, times what? 1,000 Newton what? Millimeter. Okay, yes. So from there, that is what we have to input into the equation to be able to what? Solve it. So we say we are using the 20,000 to multiply the what? 1,000. Okay. So by substitution, we are still substituting whatever we had into the what? Equation. Okay. So this is 20,000 times 10 exponent 3. So the pi we are using is 3.142. Okay. Times the shear stress. And what did you say is the value of the shear stress? The value of the shear stress was 40. Okay. 40 Newton per mm. Okay, because of this 40, it's a Newton per mm. The what? The torque must also be in Newton per mm for precision purpose, okay? They must all be in the same unit. Else, if they are not in the same unit, you can't solve it, okay? You say that your answer is not precise. So that is how the law of physics works, okay? So because of what? This guy is in what? Newton mm. This one is also supposed to be in Newton mm before you can use it to solve your work. That is why I came to change it into what? This, okay? To be able to use it to calculate for the what? Solve the problem. Okay, so from here, it's just a matter of punching it into the calculator to make life easier. Okay, you just punch it into the calculator to make life easier. Okay, so let's all take the cubic root of what? 16 times 20,000 multiplying 1,000 or 10 exponent 3 all over 3.142 times 40. Let's all point that on the calculator together. At the end of the day, what are we going to get? You realize that our answer is going to be what? Our diameter is now going to be 136. Okay, 136.55009 what mm. Okay, that is going to be our diameter. That is going to be our diameter. Take note that this guy was in what? Newton per what? Per mm. And this guy was in Newton per mm squared. Okay, so at the end of the day, Newton will take care of Newton. And in this case, we say that if the bases are the same, and they are what? Dividing, what do? We subtract the exponent. Subtract the what? The exponent. So as a result of that, at the end of the day, we had our answer to be in mm. Okay, we had an answer to be in mm because it is also affected by the what? The root, the cubic root of that. Yes. So at the end of the day, the exponent, this is what is happening to the exponent, which is leading and causing or contributing to this answer. Okay. Yes. This is going to cancel this. Okay. So the mm over there is just like this mm. Okay. Dividing this what? Mm. Okay. So at the end of the day, the first has an exponent of what? 1 at the top. The other one has an exponent of what? -2. Okay. But in indices, we say that if the bases are the same and they are what? Dividing, what do we do? We subtract the exponent. At the end of the day, we say that what? We are still taking the cubic root of that. Remember that the cubic root is also affecting it because it is still under the cubic root. The cubic root is still affecting it. Okay, so that is making the exponent to behave in a form of this way. At the end of the day, you see that their exponent is going to behave in a form of this. Okay, so at the end of the day, you realize that the 1 minus what? -2 is going to give us, is going to contribute to this. Okay, the cubic root of what? mm exponent what? 3. So the cubic root also affected it. It affected it seriously. And due to that, the answer led to what? Just an mm. Okay. So at the end of the day, this guy also came to cancel what? The whole of this. So at the end of the day, that is how we are still getting our answer in what? Mm. Take note of that. Please take note of that. So we are getting our answer to the 136 point what? 5509, which is our what? Diameter. Okay, which is our minimum diameter of the shaft. Take note that we said that the more your decimal places, the more accurate your answer. Okay, due to that, that is why we are trying to leave our answer in at least 4 decimal places so that we can be what? Precise. Okay, so that we can be what? Precise. Okay, without wasting much time, let's quickly take a look at the next question. So this is our next question. This is the example we are going to be looking at. This is our next question, and this is the example we are going to be looking at. Our last example in this aspect. Okay. And the question says that a hollow shaft of external diameter, a hollow shaft of external diameter 120 transmits 300 kilowatts power at 120 RPM. Determine the maximum internal diameter. He said we should determine the maximum internal diameter if the maximum stress in the shaft is not to exceed 60 Newton per mm squared. Okay. So at the end of the day, first of all, we say the first thing we're supposed to do is we are supposed to calculate for our given. Okay. First of all, we are supposed to look for our given, and the given attract mark. So let's all do what to be able to write the given at least. Let's all do well to be able to write the given at least so that at least we can get some marks. Okay. Yes. So we are just going to abstract the vital points to see how we can use it to make life easier. So you say a hollow shaft of external diameter. Okay. So the external diameter, I'm going to denote that by what? D subscript O. Okay. Is equal to what? 120 mm. Okay. Transmit 300 kilowatts power. Okay. At 200 RPM. Okay. So let's quickly put that down. So the kilowatt is power. Okay. Yes, we said power is measured in what? Watts. So it's a 300 kilowatts. Remember I told you in first semester level 100 that the kilo is means 10 exponent 3. Okay. So this 30 kilowatts we are seeing over here is the same as what? 300 times 10 exponent 3 times 10 exponent 3 watts. Okay. Yes. And also at a speed. Okay. Yes. At an angular speed of, and that is denoted by n. Okay. Which is what? 200 RPM. So let's all write that down. 200 RPM. Okay. So we should determine the maximum internal diameter. The maximum internal diameter. Let's denote that by what? The I. Because the question is saying a hollow circular shaft, you should know the formula that we're going to be using. It's definitely going to be the second formula that I access to write to root. Okay, in terms of a hollow circular shaft, that is the first thing that should come in mind. Okay, the formula. In some cases, you may be provided the formula. In some cases, you may not be provided. But it is always good that you prepare as a soldier. You always be ready for a battle so that you don't find yourself wanted. Determine the maximum internal diameter. If the maximum stress in the shaft is not to exceed, okay, so the shear stress is what they have given us. What is what they have given us? Our 60 Newton per mm squared. Our 60 Newton per mm squared. So from there, it implies that we just have to put down our formula in our solution and be able to use that to derive the ones that we are supposed to what look for. Okay, so this was equal to what? 60 Newton per mm squared. Good. So from here, we are moving to our solution. We are moving to our solution. So the first thing we are supposed to do is that we put down our formula down, and we say that the formula for finding for the hot torque transmitted by a solid, a hollow circular shaft is what? T is equal to, our T is equal to pi over 16 times the hot shear stress times hot bracket open, the hot, the external diameter exponent 4 minus the internal diameter exponent for all over hot, the external diameter, okay, which is written as this. Anywhere you see this attribute O means external diameter, which is written as this. Okay, so from the formula, it implies that we have to look for what? Our hot internal diameter, which is the DI. So we have to make DI the subject of all this relation to be able to what? Find for it. Okay, but before that, let's come and see if we know our hot, the shear stress from the given it. We realize that the shear stress is what is known. This is it. But the torque is not known. So it means that we have to find for the hot torque before we can be able to, we can even proceed with our calculation. Okay. In the third formula I told you to write, you realize that we also said that what? Our P, okay, our power is equal to what? Angular speed times the what? Angular speed at the end of the day, which we got to find out that uh, the formula was angular speed times the torque. Okay, so from there we also realized that that was the formula that torque can be derived from. Okay, and that formula is giving us what? 2 pi multiplying the what? The speed all over 16. Okay, this is the formula. Okay, yes, and then the real formula itself was this: the P times the what? Angular speed times what? The T. Okay, where we said that the what? The omega is equal to what? 2 pi over what? N all over what 60. So that is what we came to substitute into this to get this formula. Okay. Yes. So you can also jot that down so that life can be more easier for you. Life can be more easier for you. So from there, we have to just make our T the subject, find for T and use it to what? Calculate our problem. Okay. Yes. But before that, DI is what they say we should find for. So it means that we have to make DI the subject of the relation even first before we say that we are going to look for the other person. Okay. So let me quickly clean this and let's make DI the subject of the relation. Since that is what we are supposed to find for first, so that we can navigate our way easier. So this that we are having over here is the same as this. Okay. Take note. This relation you are seeing at the top is the same as this. Don't get confused. They are all the same thing. It's the same as this. Multiplying what? All of this. This what? T. This is the same as this. Okay. This is the same as this. They are the same thing. So that can be written as this. And also, this can also be written, can further be written as this. Okay. Just take a close look and have a look at how I'm going to make the change of what subject. Okay. Yes, this is also the same as what this. Don't get confused at all. With the laws of indices, I'm just trying to play with the what symbols. Okay. To see who we can be able to make the subject. Yes, this is also the same as this. Okay, multiplying this, multiplying the external diameter. Okay, so it is just the same thing. That the formula, the first formula we wrote, you can write it in so many ways. Okay, yes, so it is also the same as just this. Okay, I hope you can all see what I'm seeing. Okay, in the physics world, that is what is happening. That is what is happening. Okay, so from this concept, it means that we can now use the concept of what? Cross multiplication, okay, or LCM to be able to what? Make our DI the subject, okay. Whatever I wrote, I've written from step 1, 2, and 3. There's no difference. They are all the same thing, okay, but just that it has been separated. That is why you are seeing it as something like that, okay. So from here, you can choose to use the concept of cross multiplication, or you will make the denominator the LCM and use it to multiply both sides. Okay, yes. So you can choose to use the lowest common multiple approach, or also use the approach we are adapting over here to make life easier. Okay, so even this at the top is also the same as this. In short, this is just also the same as this. Okay, U 4 into the outer diameter. 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 4 into the outer diameter Okay, this is the inner diameter. It is all the same thing. All over what 16 multiplying the outer diameter. Okay, okay. So from here, or this concept, you can use the knowledge of what uh, cross multiplication to be able to just um, navigate our way easier. This guy is going to multiply this. This one is also can be multiply this over here. This guy already, I told you that in the previous word, it has a denominator of 1, but we don't write it. Okay. Yeah, so any number you see is divided by 1. Or it could be an alphabet or anything. So these things come to multiply this 16 d subscript O. Okay. So that is going to be T hot. T times what? 16 times our D. Okay. That is O, which is equal to what? Pi over what? Pi multiplying tau times our D subscript O exponent 4 minus the hot inner diameter. Okay. Minus the outer diameter minus the inner diameter. So all of these two what? All of these two is multiplied. Is multiplying what? 1. Okay. All of these two is multiplying the 1. Okay. So at the end of the day, you realize that um we are going to be getting a relation such as what? Our 16 d subscript O. Okay. Or it could still leave it like that. It will still be the same thing. T hot 16 uh, multiplying the outer diameter equal to the hot, the pi times the tau, equal to the pi times the tau, also multiplying the hot, the external diameter exponent 4 minus the hot inner diameter. Okay, please take a pen and a paper and try to write as I also write along. Okay, to aid your understanding. Okay, so from here, you realize that we can expand the bracket. Okay, from here, we can now expand the bracket. Okay, so let's quickly expand the bracket so that we can see our next way forward. This step is still going to repeat. This step is still going to repeat. This step is still going to these are dots, okay, and it signifies, or it signifies multiplication. Okay, yes, okay, it's equal to, if you want to expand this bracket, it's the first one is going to be what? Pi what times tau. Okay, I'm going to multiply our external diameter exponent 4. Okay, and these people that are outside are still going to multiply the other one minus what? Pi times the what? Tau, all multiplying the what? Inner diameter 2 exponent 4. Okay, so from here, the next thing we are supposed to do is just what? Group like things. It is this di that we are looking for. It is the inner diameter that we are looking for. So we just have to make it the subject so that we can find our way. Okay, so from here, let's quickly make that the subject. Okay, so we're making that the subject. We have to move this guy to this side. So T multiplying 16 times the what? Outer diameter is going to multiply. If this guy come over here, it's going to become negative. Okay, so it's now going to become minus what? Pi times what? Tau times the external diameter exponent 4. Okay, which is equal to what? Minus what? Pi times the tau. Also multiplying what? The inner diameter exponent 4. Okay, inner diameter exponent 4. So from relation, you can just make the di the subject. Okay, from here, because you want di to stand alone, so you have to divide both sides. Okay, so but I want to repeat this step one more last time again, so that after the division, you can have a clear look at what is happening in here. Okay, yes. So this is going to become like this. You have to divide both sides. You have to divide both sides by the same thing. So I'm going to divide here. I'm going to divide here by this because it is di that I want. So I divide here by what? Minus pi tau. And also come and divide here by what? Minus what? Pi what? Tau. Okay. From relation, we realize that this guy is going to what? Take care of this. Okay. And at the end of the day, you are left with what? Di exponent 4 is equal to the whole of this. But take note that this we are seeing over here is the same as this. Okay, what we are seeing at the top over here is the same as this. What we are seeing at the top is the same as what I'm writing over here. Have a look. This is also the same as this. This is also the same as this. Whatever you are seeing at the top is the same as this. So this was Ti exponent 4. Good. So whatever you are seeing over here, because these guys have been cancelled, this is the same as. Don't get confused. Don't get confused. Okay. So from here, what is going to happen? From the laws of physics and indices, these two people are going to take care of themselves. Okay, this is going to cancel this again. So from there, you're going to be left. You're going to be left with these two relations. Okay, but I forgot. I didn't bring the d. Okay, I didn't bring the d. So the d is this, the outer diameter. Yes. So this is the outer diameter. Okay. So so we're going to be left with this. So at the end of the day, this relation we are seeing over here is going to end up becoming like this. Okay, this negative over you are seeing over here, this is also just the same as this. Okay, T multiplying 16 multiplying what our external diameter. Okay, multiplying our external diameter all over what pi times the tau, all over pi times the tau. These formulas will not be proven for you, and they will not be given to you. So it is good that you know how to what make change of subject to be able to find to be able to find a value. Okay, if you're not able to do the change of subject, no one will provide you a formula start, so you will struggle. So please do well to learn it so that life becomes easier for you. Okay, and at the end of the day, this negative is going to cancel this what negative to make it positive. Okay, so this is going to become plus what our d subscript o exponent what 4. Okay, di what cube exponent 4. I told you that if a is equal to b, it means that b is equal to a. Okay, so if we want to rearrange this and find for uh, our d, it means that we are going to our di is going to become what we have brought the di to the left hand side, and that is going to become what we can group this and make the positive one come first. It is still the same thing. That is what d exponent what 4 subscript o still minus or because the negative is affecting this one. Still minus what t times 16 d subscript o all over what pi times the tau. Okay. So from here, the next thing I'm supposed to do like is d we are looking for. We're not looking for d cube. Okay, this means that this the 4 of these are this side. Okay, so it is just one of them that we want. So we have to divide, we have to take the nth root of what? Both them. Okay, this is the nth root. Okay, but in this case, the value of our n is equal to what? 4. So this implies that we divide here by what? We are going to divide here by what? We're going to divide here by, we are going to take the nth root of both sides and where the n is what? 4. So finally, we realize that this is going to cancel this. This 4 is going to cancel this root. And then finally, we can say that our external diameter can be calculated for using the formula this. Okay. So finally, we say that our external diameter di. Okay. Finally, we say that our external diameter, our internal diameter, okay, is equal to this. So we just made di the subject. Okay. We just made di the subject. So we can now come and substitute anything we had into the equation to make life easier without writing the notes along as I teach. It's going to make the learning difficult for you. Okay, you will have to be pausing and be going back. But if I'm writing and you are also writing, you have a full list, so you can just quickly cross check anything you want to cross check at any point of time in the lecture. Okay, so that is how our final relation is going to become. Okay, yes. So that is it. This is not too far from it. So we just substitute our values into the equation to make life easier. Just one question, or we have to make change of subject before we can be able to solve. Other than that, we are gone. Okay. So we realize that we have our outer diameter, our power has been given to us, but the T is not given to us. So it means that we have to go and calculate for our what? Our T. Okay. All these values are known. The outer diameter is given, the shear what stress is given, but our external diameter is also given, but our T is unknown. Okay. So our T is what we don't what? Is what we don't know. So it means that from the formula we learned that we said that what our P is equal to what? From the formula we learned that we said that our P is equal to what? 2 pi nt over 60. 2 pi nt all over what? 60. We have to make just T the subject so that we can be able to find for T. Okay, and from transposition of formula, you realize that this P is going to what? Multiply the what? 60. Okay, and at the end of the day, this is going to constitute what? This is also going to multiply a 1 under the P. Okay, so if you divide both sides by 2 pi and you realize that finally your value of your T is going to become what? Our T is going to become what? If you make T the subject, you realize that your T is going to become P multiplying 60. Okay, all over what? 2 pi, all over 2 pi n. Okay, all over 2 pi n. So let's just quickly substitute whatever we have into the equation to see how best we can travel. Okay, so our P is equal to what? They say our P was equal to 300 kilowatts. Okay, so 300 times 10 exponent 3. The 10 exponent 3 is the kilo. Okay, times the 60, times the 60, times 60 all over 2 times 3.142 times what? The n. And what was the value of our n? What was the value of our n? The value of our n given to us was 20. Okay, so let's use that to calculate for uh, the value of our n given to us was 200. It was rather 200. So let's quickly substitute that into our figure to calculate for our values. Okay. Okay. So the value of our n was 200. 200. Good. At the end of the day, we realize that the answer we are going to be getting for our torque is going to be what? If you punch this into the calculator, let's all do this together. Let's all do this together. 300 times 10 exponent 3. Okay. Times 60 all over 2 times 3.142. 200. And what are you going to get? What are we going to get? You realize that you're going to get 14322.3. 0.784. Okay, you're going to get 142.2.784. Okay, but you realize that this answer is going to be in what? Newton meter. Okay, due to that, before we can use it to even calculate for our diameter, we have to convert it into what? Mm, and in converting it into we have to multiply it by what? 10 exponent 3. Okay, so that is going to make our final answer to become T to be equal to what? Which is the top to be equal to 142.08784 times what? 1000. 1000 is the same as 10 exponent 3 Newton what? Mm. Okay, good. At the end of the day, now we know the value of our top. We now know the value of our top. Okay, and this in its simplest state is also the same as this 14322 point. Points will not come anymore if you multiply the whole of this. The is going to shift the zeros. Okay, the exponents of the tens are going to shift the zero, and it's going to become like this. We're going to get 14322.090 Newton mm. Good. From here, we can now come and put everything into our general equation. Okay, what we had over here, we said that our di is equal to what? Our di. We said that after making di the subject, we said that our di was equal to what? We took the n to it, and the value of the n was what? 4. Okay, where the d was what? The external diameter had an exponent of 4 minus what? 16. Okay, t multiplying the 16 d. So we had what? T multiplying the 16 times the what? Outer diameter all over the pi, also multiplying the what? The tau. So at the end of the day, let's just substitute in our values and then get our final answer. And let's wrap up for the day. So the value of our outer diameter was what? It was 120. Let's all do that together. 120 all exponent 4 minus the t. The value of our t was 14322.7 times the 16 times the what? Outer diameter. And the outer diameter we said was 120. Okay, it's just a matter of substitution. The power we are using is 3.142 multiplying the tau, and that was the shear stress, and the shear stress given was what? 60. Okay, so at the end of the day, At the end of the day, our answer is going to be just uh, MN. Okay. Yes, our answer is just going to be MN. So let's all point this together on the calculator. You can press shifts and X exponent box on the calculator. You can see that the first one you put 4 over there, you shift your cursor down, and then you feed in whatever you have over here into the calculator. Okay. Better still, you can see your colleagues so that they teach you how to do that. Or you can even watch the YouTube video on how to take the end root of something on the calculator so that uh, you don't struggle in the examination hall. Okay. You have to prepare adequately before the party so that on the D-Day, life can be very, very, very easy for you. If you fail to plan, you're actually planning to fail. So please, in a very big please, let's try our possible best so that we can all come out successfully at the end of the semester. Okay, we have all struggled enough, and now that the semester is getting to an end, last days are very dangerous. Okay, so let's try our possible best to take very good care of ourselves so that we don't fall into any temptation. Okay, after punching this on the calculator, you're going to get what? 88.554. Okay, so I'm just writing 4 decimal places just for my answer to be more precise. Okay, as simple as that. There are more decimal places, but I choose to just adopt the 4 decimal places method. Okay, so if you found this video very useful, just don't forget to throw $1 on my name anytime you meet me in person. Okay, yes, thank you very much for your time also. I really had a nice encounter, a nice experience with you all this semester. I pray that God bless you all so that we can all come out successfully. Okay, yes, so don't forget to see me in groups, in person, one on one, in case you encounter any challenges or you still wish I could throw more light on whatever we have learned. Okay, or you still wish I could throw more light on whatever we have learned. Do well to see me in groups in person so that I can tell you more. Thank you very much once again. Bye bye.